Hello everyone. Having discussed the experimental gas laws in the previous lecture, now we are going to discuss the equation of state. So let's see what is equation of state and what is the concept of ideal gas. Now let's start with this experimental gas laws. We have a gas which is at state 1. Now this is to be converted into the final state. This is initial. It is final state. Now same gas, we have a gas A. Now this gas A is to be taken from this initial state to the final state. In the initial state, the pressure of the gas, let's suppose this is Pi, volume of the gas is Vi. Now the amount of substance in this initial state is N. Now this initial gas is to be converted into the final state in which the pressure is Pf, volume is Vf, amount remaining same, temperature of the gas, suppose this is a T1, temperature suppose this is a Tf. So this is the initial state of the gas A. Now having pressure Pi, Vi, Ti, amount N is to be taken to the final state having pressure Pf, volume Vf, temperature Tf, that is same gas A. Now this change of state from initial to the final can be taken in two different routes, either by keeping the temperature constant or by keeping the pressure constant. So we can go through either by keeping the temperature constant or by keeping the pressure constant. So first, this gas A is converted to an intermediate state. This is intermediate state. Now let's assume a case in which this gas from initial to the final is carried out at initial to the intermediate state is carried out at temperature constant. So if temperature remaining constant, the temperature at the final intermediate state, this will be Ti, amount will remain as it is. Now temperature remaining constant, we have Boyle's law will be applicable. So according to Boyle's law, pressure and volumes are inversely related. Now when we change this gas from initial state to intermediate, pressure changes to Pf and volume changes to some intermediate volume Vr. And from this intermediate to the final state, change from intermediate to final state, this is carried out by keeping pressure constant. So if pressure remaining constant, then Charles' law will be applicable. So in the final state, volume is changing from Vr, that is intermediate volume, to the final volume V, and temperature from Ti to the final temperature Tf. pressure remaining constant. So let's say this is step 1, this is step 2. So we are changing from initial to the intermediate and from final intermediate to the final state. So look at this step 1. So in step 1, temperature remaining constant, amount of gas is constant. So temperature constant, N constant. So Boyle's law is applicable. So if Boyle's law is applicable, then we have this relationship Pi Vi is equals to Pf Vr. So this is intermediate volume. So therefore intermediate volume Vr is equals to Pi Vi divided by Pf. Let this be equation A. Now we have defined intermediate volume, that is Vr. Now look at this step 2, second step. Now in this step 2, pressure remaining constant and amount of gas also remaining constant. So if pressure and amount of gas remains constant, then Charles' law is applicable. So according to Charles' law, volume and temperature are directly proportional, or we say Vr by Ti, to pressure remaining constant, will be equals to Vf divided by Tf. So we have this relationship. Now we know the value of Vr. So using the value of Vr in this equation, we obtain Vr is Pi Vi by Pf into Ti is equals to Vf divided by Tf, or we can say Pi Vi divided by Ti is equals to Pf Vf divided by Tf. So Pi Vi by Ti, that is initial value. Pf Vf by Tf, that is the final state. So if you look at this equation carefully, the ratio of pressure into volume to that of temperature, initial is always equals to the final value. So this means pressure into volume divided by temperature is always a constant. Is always a constant, which is given as K. So this equation, pressure into volume divided by T, which is always a constant, or we say Pi Vi by Ti equals to Pf Vf by Tf. This equation is what we call as equation of state. That means whenever a gas changes its state from initial to the final state, then the ratio of product into volume to that of temperature will always remain a constant. This is what we call as equation of state. Now the question is, what is the nature of this constant K? Nature of constant K, because we have to define this constant K. Now look at this. Pressure is a quantity which is independent of the mass, and this mass independent quantity is known as intensive variable. Similarly, temperature of a substance is independent of the mass of the substance. So pressure as well as temperature is mass independent quantity. Whereas volume is a mass dependent quantity. So this mass independent quantity multiplied by a mass dependent quantity is always a mass dependent quantity. That means if the left hand side is a mass dependent quantity, then the right hand side must also be a mass dependent quantity. That means, look at this, pressure and temperature. This is mass independent. So mass independent quantity is known as intensive. So this is intensive quantity. Volume is mass dependent. So mass dependent quantity is known as extensive quantity. So the product of pressure by volume, so pressure by temperature into volume, this is a mass dependent. So if, as I told you, if the left side is mass dependent, then K must also be a mass dependent. Therefore, K should also be a mass dependent. So we know if left side is mass dependent, then K should also be having a mass dependent. So this mass dependent term K can be written as proportional to N, where N is number of moles of gas. So we say if K is a mass dependent, obviously this is depending on the number of moles of gas, because number of moles of gas is mass by molecular mass. So K depends on the number of moles of gas, or we say K is equals to N R. So where R is a universal constant which is independent of the nature of gas. So R is universal constant independent of nature of gas. So we have this K, which is a mass dependent quantity. Why this is mass dependent? Because volume being mass dependent, pressure by temperature into volume should also be a mass dependent. So K is a mass dependent. So we say K is proportional to N, number of moles of gas. So therefore K is equals to NR. R is a universal constant which is also known as gas constant, which is independent of the nature of gas. So we have this value of K. Now using the value of K in equation B, so therefore from equation B, should I write this? So therefore from equation B and C, we get pressure into volume divided by temperature, which is equals to K. So K is equals to NR. So therefore look at this, PV is equals to nRT. So pressure into volume of gas is always equals to number of moles of gas, universal constant R, and temperature measured in terms of Kelvin scale. So this equation is a very famous equation or a well-known equation, which is known as ideal gas equation. So, what is ideal gas equation? Pressure into volume is equals to number of moles into R into T. PV is equals to nRT is a well-known or a famous equation which is known as ideal gas equation. Or now the question arises, if someone asks you what is ideal gas? So a gas is an ideal gas if that gas strictly follows the ideal gas equation, that is pressure PV is equals to nRT. So any gas which follows this equation strictly at all pressure and temperature condition is defined as ideal gas. And now look at this. This ideal gas is an idealized concept because not a single gas, none of the gas present in this universe is perfectly ideal. So all these gas that is present in this universe are non-ideal gas or known as real gas. So these real gas under some restricted conditions shows ideal behavior. So we are taking of this idealized concept. So this what I am trying to convey is the experimental gas laws that we have discussed so far. These experimental gas laws is applicable only for ideal gas. These gas laws are not applicable to the real gas. So we have this. So ideal gas. So a gas which strictly follows ideal gas equation at all temperature and pressure condition. That gas is known as ideal gas. So all gas, none of the gas is ideal but is a real gas. So this ideal gas is an idealized concept because none of the gas present in universe is ideal. These gases are non-ideal or real gas. So real gas means the gas which does not follow this ideal gas equation. Or ideal gas equation is any gas which shows this equation strictly at all possible temperature and temperatures conditions. So as I told you, none of the gas is ideal gas. All these gas that is existing on in this universe is a real gas or non-ideal gas. And these real gas approaches ideal gas under restricted conditions of pressure and temperature. So we have this real gas. Real gas tends to ideal gas, or a gas approaches ideal behavior under some restricted condition, and that restricted condition is, what is the restricted condition? At low pressure and high temperature. So at very low pressure and very high temperature, a real gas approaches ideal behavior. But if pressure is increased or temperature is decreased, then this shows deviation from ideality. So we'll discuss why there is a deviation from ideality in the next few lectures. But for your information, none of the gas is ideal. These gases are known as non-ideal gas or real gas because they does not follow this equation strictly, and these gases follow this equation strictly under some restricted condition, and that restriction condition is they should be having a low pressure or high temperature. So only under low pressure and very high temperature condition these real gases approaches to that of ideal behavior, and they will try to follow this equation strictly. Now we have this. Now we have defined this R. These are, as I told you, this is known as universal constant, independent of nature of gas, independent of the nature of gas. So if you change the nature of gas, means this R will be same for whether this is ideal gas or whether this is real gas. This is hydrogen, nitrogen, fluorine, yeah, nitrogen oxide, sulfur dioxide. For any gas, if we change the gas, then the value of R will not change because this is always a universal constant independent of the nature of gas. Now these R is sometimes known as gas constant. Now this has got different values. This is equals to 8.314 joule per Kelvin per mole. So this is a standard value in standard unit, joule per Kelvin per mole. This is equals to 0.08314 bar dm cube per Kelvin per mole. This is equals to 0.082 atm liter per Kelvin per mole. This is equals to 1.98 calorie per Kelvin per mole. So approximately this is 2 calorie per Kelvin per mole. So these are the different values of R, and of this the standard value is 8.314 joule per Kelvin per mole. That is the standard units. Joule per Kelvin per mole, this is standard unit. Now we are simply saying that this is universal gas constant which is independent of the nature of gas. Now the question is, what is the nature of this R? Let's see. Nature of R. Now we have this equation PV is equals to nRT. So from this equation, ideal gas equation, R is equals to pressure into volume divided by N into T. Now in earlier class we have defined pressure into volume has got the dimension of energy. The dimension of energy and the dimension of pressure and volume are same. Pressure is force per area, volume is area into length. So this is force into distance, which is defined as work done. So work done is nothing but the energy. So we have this pressure and volume, that is energy divided by N number of moles, mole, temperature in Kelvin. So if you look at this equation very carefully, these are is nothing but the energy that could be obtained from 1 mole of a gas when the temperature changes by 1 unit. So we have a gas. If this gas contains 1 mole and this 1 mole gas containing substance, if temperature increases by 1 unit, then what is the energy that could be obtained from this species? That is known as the universal gas constant. So therefore, defining this, we say this is the total energy that could be obtained from 1 mole of a gas when its temperature changes by 1 unit. So how much energy that could be obtained if temperature increased by 1 unit containing 1 mole of a substance? That is defined as the universal gas constant R. So this is independent of the nature of gas, and this has got this different values. So either if you can remember this, it's well known, but in most of the case values will be given to you. If not given, then you can memorize these values also. So this is universal constant, which is often used in numerical problems. So now coming back to this equation D, let's try to modify this equation D further. Now this equation can be written as N by V R T. Now if you look at this, if volume is measured in terms of liter and number of moles, then number of moles per unit volume, this is defined as the concentration of the gas, where this C is equals to concentration, which is equals to number of moles per unit volume. So this is measured in terms of molarity. So if the concentration of the gas is given, then we can also write this modified equation, that is pressure is equals to the concentration into R into T. But while using this equation, we have to keep in mind, since the concentration is measured in terms of liter, so these R must be in terms of liter and pressure must be in terms of atm. So this unit must correspond. Now taking this equation further, we have, look at this, P is equals to N, number of moles is mass divided by molar mass into volume, R T, number of moles is mass divided by molar mass. This is mass of gas taken, this is molar mass of the gas. Now we have a term mass by volume is defined as density. So therefore pressure is equals to density RT by molar mass. So D is equals to density, that is mass by volume. So if you look at this, pressure is directly proportional to density of the gas at a given temperature. Pressure is directly proportional to the density of gas at a given temperature for a gas. So for any given gas, at a given temperature, pressure is directly proportional to the density. So this equation, pressure is equals to density RT by M. This is equation F. So this is another modified equation of ideal gas. So we can, the most common equation is PV is equals to nRT, but under some conditions, if the question involves density, then we can also use this density equation. This is also ideal gas equation. So pressure into molar mass is equals to density into RT. Or if the concentration of the gas is given, then we can use this equation. Pressure is equals to CRT. C is the concentration measured in terms of number of moles per liter, that is molarity. So this, while using this equation, as I told you, we have to keep in mind the values of R. So values of R and the values of pressure has to correspond. So density is mass per unit volume, though we have used volume in terms of liter, then this pressure must be in terms of liter. So this is equation of state and ideal gas equation. So by use of this equation, we can solve problems. So after discussing these gas laws and equation of state, now we are going to focus on how to solve the numerical problems and how, which by just looking at the data, how we can predict which equation is to be used. So coming to the numericals, based on this experimental gas laws and this ideal gas equation. Numericals. Let's take some example. Suppose look at this, we have a container. This is a container. We have a stopper. This is connected to another container. So this container, suppose this contains a gas, suppose a gas, argon gas, and this is at 15 ml. So we have 15 ml, a container whose volume is 15 ml. This contains argon gas. Temperature is suppose 30 Kelvin. Now this is connected to another evacuated. This is evacuated container whose volume is, suppose this is 235 ml. So this contains argon gas. Volume of container is 15, so this is the volume of gas. Now this is the temperature. Now what we are doing is, now we open the lid. This is the lid. Now we open the lid and gases are allowed to pass from this container A to container B. Lid open. So after opening this lid, gas moves from this container A to evacuated container B. Temperature remaining constant, so still temperature is 30 K, that is 30 Kelvin. The final pressure of the gas is 750 millimeter of mercury. Then the question is, what was the initial pressure? So I repeat the question again. So we have argon gas which is enclosed in a 15 ml container. This container is connected to an evacuated container whose volume is 235 ml. So we have a lid, it is tight. Now on opening this lid, gas moves from this 15 ml container to 235 ml container. So gas will occupy this total volume. Now after this opening of the lid, the total pressure of the gas is 750 millimeter of mercury. Now what was the initial pressure of argon in this container? So now look at this, temperature remaining constant. So if you look at this, temperature remaining constant, only argon gas is allowed, that argon gas which was enclosed in this container. So the amount of substance is again constant. So question clearly says only this gas which was present in this container is transferred to this container. So N constant. So if temperature constant, N constant, then which law is applicable? Boyle's law is applicable. So if the Boyle's law is applicable, then we have this PIVI is equals to PFVF. Now we have to find this PI. So therefore PI is equals to PFVF divided by VI. Now we have the values of this PF. So PF is 750 millimeter mercury. Volume final. So after opening this lid, gas occupies this volume as well as this volume. So the total volume will be 15 plus 235 ml divided by initial volume is 15 ml. So this is the initial pressure. Now the final pressure was measured in terms of millimeters of mercury. So this must be in terms of millimeters of mercury. So we have this 750 millimeter of mercury into, this is 250 divided by 15. So this is the initial. Now look at this. Obviously look at this. Volume increases, so pressure has to decrease. So initially this was a very small volume. Now the volume increases to 250. So pressure volumes are inversely related. So initial pressure should have been very high. So this comes out to be 50. So this is millimeter mercury. So volume increase, pressure decrease. So the whole process, what I'm trying to show is temperature remaining constant and remaining constant. So Boyle's law will be applicable. Second thing, after opening this lid, gas will occupy this volume as well as this volume, assuming this volume is negligible. So the total volume is these two volumes. So this is 235 plus 15, that becomes the final volume. So don't say that the final volume will be only 235, because after opening some gas will be found in this container as well as this container. So this is the total volume, that is 15 plus 235 ml. So this is one numerical based on Boyle's law. Let's take up some more numericals. second question. Question says 200 ml of a gas at 30 K is compressed by increasing the pressure by 5%. Question says calculate the volume of the compressed gas. At 30 K. So question says, look at this very carefully. We have a gas. This gas is compressed. The same gas is compressed. So amount remaining constant. Question clearly says initially this was at 30 Kelvin. Now this is compressed to the final volume, keeping the temperature constant. So first thing that we have to keep in mind, what are the constants, means which terms are remaining constant in this process, compression of the gas. Temperature remaining constant, this is clearly given here. Initial gas was 30 gas, after the compressed gas is again compressed at the same temperature, so temperature remaining constant. Second, same gas is compressed, so N is again constant, so temperature constant, number of moles constant. So which law is applicable? Boyle's law will be applicable. So if the Boyle's law is applicable, then Pi Vi is equals to Pf Vf. Now look at this. Vi, initial volume of the gas, is 200 ml. Let the initial pressure be Pi. This is initial pressure Pi. Let this be P pressure. Suppose this is P atm. Then question says the final pressure increases by 5%. So final pressure is Pi plus 5% of Pi. So this says Pi is P plus 5%. So this is 0.05 times P, or we say this is 1.05 P. So this is the meaning of 5% increase in pressure. So this is the final pressure. Now question says what is the final volume. Now we have this Boyle's law. So according to Boyle's law, we say Pi Vi is equals to Pf Vf. So therefore, now look at this, volume is decreased, pressure is increased. So this volume should be less than 200 ml. So therefore, Vf is equals to Pi Vi divided by Pf. So Pi is P, Vi is 200 ml. This is divided by 1.05 P. So P and P will cancel now. So this will give the volume, and this volume must be in terms of ml. So this value will always be less than 200 ml. So we compress the gas, pressure increase. So this is a compression process. So the volume has to decrease. So this is question number 2. Now take another example. take this example. Calculate the percentage increase in temperature of a gas when it is heated at constant pressure, when it is heated at constant pressure to occupy 20% increase in volume. So question says, what is the percentage increase in temperature of a gas when the gas is heated at constant pressure to occupy 20% increase in volume? So first thing that we have to keep in mind is, while going through the question, one thing is clear: the pressure of the gas remaining constant. The same gas is heated, keeping pressure constant. So we are heating the same gas. So again, n number of moles of gas remaining constant. So therefore, look at this: pressure remaining constant, number of moles of gas remaining constant. Then which law will be applicable? Charles' law will be applicable. So we have to apply Charles' law. Now, if suppose initial temperature is Ti, final temperature is, we have to find out the final temperature, then we have to find the percentage increase in temperature, and pressure increases 20%. So therefore, according to Charles' law, we have, look at this, Vi by Ti is equals to Vf by Tf. So therefore, look at this, we have to find out the value of Tf. Now Tf is equals to Vf divided by Vi into Ti. So increase in volume, plus 20% increase in volume. So therefore, the final volume is initial volume plus 20% of the initial volume, that is the final volume, divided by Vi into Ti. So this is 1.2 Vi divided by Vi into Ti. So Vi will cancel out. So this comes out to be 1.2 times initial temperature. So the final temperature is 1.2 times initial temperature. So therefore, increase in temperature. What is increase in temperature? That is final temperature minus initial temperature. So this is 1.2 Ti minus Ti. So this comes out to be 0.2 Ti. So therefore, percentage increase is increase in temperature divided by initial temperature into 100. So increase in temperature is 0.2 Ti, initial is Ti into 100. So this is 20%. So if the volume increases by 20%, keeping pressure constant, then temperature should also increase by 20%, because volume and temperature is directly proportional according to the Charles law. So this is how we apply Charles law. Let's take up some more examples. Number 4. Question says a gas occupies 300 ml at 27 degrees centigrade and 730 mm pressure. What would be its volume? Would be its volume at STP. So we are using a term STP, standard temperature pressure. So first let's define what is standard temperature pressure. STP, standard temperature pressure. So here in STP temperature is 273 Kelvin or 0 degree centigrade, which is equals to 273.15 Kelvin, and pressure is 1 atm. Now pressure has got different unit. So let me give you different units of pressure. Pressure is equals to 1 atm. So this 1 atm is equals to 760 millimeter of mercury, which is equals to 76 centimeter of mercury, which is equals to 760 torricelli, which is equals to 101.325 kilopascal. So Pascal is the standard unit of pressure. This is equals to 1.01325 bar. So these are the different units of pressure that we often use in this type of numerical. So I'll give you the relationship between all this. So STP is when temperature is 0 degree centigrade, that is 273 Kelvin, and pressure is 1 atm. So for all practical purpose, 1 atm is approximately equals to that of 1 bar. So we can take this. So a gas occupies 300. So now look at this. Initial volume. This is 300 ml. Initial temperature is 27 degrees centigrade. So this is 27 plus 273. Take it approximately 273. So this is 300 Kelvin. Initial pressure is 730 millimeter of mercury. Then question, what is the final volume? STP. So at STP, final pressure, that is 760 mm, because we have 1 atm at the STP. Final temperature, this is 273 Kelvin. Then what is the final volume? So this is STP condition. Now look at this. Pressure, temperature and volume is given. We have the same gas changing from this initial state to the final state. Then we have this equation of state. So from equation of state, that is Pi Vi by Ti is equals to Pf Vf by Tf. We have to find the value of Vf. So therefore Vf is equals to Pi Vi by Ti into Tf by Pf. So we have all the values. So just insert the values. Pi, we have this Pi 730, Vi 300, TF, that is 273 divided by TI is 300 into PF is 760. So this is volume. The initial volume was in terms of ml, so this must be in terms of ml. So this will automatically cancel out. This and this cancels out. So this is the final volume or the volume at STP. So this is now, since pressure, volume, temperature of the gas is given, and in the final state again pressure, volume, pressure and temperature is given, we have to find the volume. So we have to use this equation of state, that is PV by T is always a constant. So number 5. A sample of gas occupies 10 ml, 10 liter under the pressure of 1 atm. So suppose we have a sample of gas. This gas, the volume is 10 ml, so 10 liter, and pressure is, this is the volume initial, pressure initial, that is 1 atm. So this sample of gas in this changes to the final state when pressure is increases to 2 atm. So this is initial, this is final state. So initially gas was having 1 atm, 10 liter volume. Now pressure increases to 2 atm, volume we have to find out, remaining temperature remaining constant. So temperature remaining constant. So we are changing the state of the gas, keeping temperature constant. Same gas, pressure is changed, keeping temperature constant. So temperature remaining constant, number of moles of gas remaining constant, then under this condition Boyle's law will be applicable. So according to Boyle's law, P1 Pi Vi is equals to PF Vf. So therefore Vf is equals to Pi Vi divided by Pf. So Pi is 1, Vi is 10, Pf is 2. So pressure increases means volume must be decreased. So this is volume 5 liter. So initially volume was 10 liter, now this decreases to 5 liter, and correspondingly pressure is increased. Look at this. A sample of gas, suppose we have a sample of gas. This sample of gas is contained in a container such that the volume is 600 ml. Initial temperature is 27 degrees centigrade and initial pressure is 1 atm. So we have a sample of gas occupying 600 ml at 27 degrees centigrade with pressure 1 atm. What will be the volume at 127? Now this is initial. Now this changes to the final state. So at this final state, the final temperature is 127 degrees centigrade. Then what is the volume? Final volume. Question there says final volume pressure is 180, means pressure remaining constant. So we have a sample of gas which is to be changing from this initial to final state. In this process, pressure remaining constant. The same gas is undergoing change from initial to final under constant pressure. So pressure remaining constant and number of moles remaining constant. So which law is applicable? Charles law will be applicable. So according to Charles law, we have VI by Ti is equals to Vf by Tx. Now look at this: initial volume, temperature, final temperature, volume. So we have to find this final volume. So keep in mind, these temperatures should be converted into degree centigrade, should be converted into Kelvin. So for all numerical problems involving temperature, temperature should be converted to Kelvin. Can please keep this thing in mind. So therefore look at this: final volume is Vi by Ti into Tf. So initial volume is 600. Final temperature is 127 plus 273 divided by 27 plus 273. So 600 into 400 divided by 300. So we have looked at these two. So So in final volume is 800 ml. So pressure remaining constant if temperature is increased, volume is increased. So according to Charles law, volume temperatures are directly proportional to each other. So take some examples. A cylinder containing cooking gas So we have this question: a cylinder containing cooking gas can withstand a pressure of 14.9 atm. That means the maximum pressure that could be held by this gas is 14.9 cylinder. Pressure of a cylinder, a given cylinder at 12 atm is 12 atm at 27 degrees centigrade. Now, due to a sudden fire in the building, temperature starts rising. Then at what temperature will the cylinder explode? So maximum pressure that could withstand by the gas cylinder is 14.9. If pressure exceeds this 14.9, obviously cylinder will blast. So we have to find at what temperature the cylinder will explode. Now look at this question. Seems to be very tricky, but if you look at this question very carefully, we are considering a cylinder. So during the process, the volume of cylinder will remain constant. So volume remains constant. Now the gas inside the cylinder, the quantity also remaining changed. So number of moles also remains constant. So volume remaining constant, number of moles of gas remaining constant. Then which law will be applicable? Gay-Lussac's law will be applicable. So according to Gay-Lussac's law, Pi by Ti is equals to Pf by Tf. So now look at this. This cylinder will explode if pressure reaches the maximum pressure that could be withstood by this cylinder. So therefore Tf, that is the temperature at which the cylinder will explode, that is Pi by Ti into 1 by Pf. So Pi is 12 Initial temperature is 327 plus 273, 300 into final pressure, that is the maximum pressure, that is 14.9. So when this pressure reaches this pressure, then that will be the temperature at which the cylinder is likely to explode. So this temperature should be the temperature at which the cylinder will explode. So these are some of the examples at which we can use this ideal gas equation, that is experimental gas law. So we'll take up with some more examples in next video lecture.